Okay, so previously we talked about parametric equations for surfaces, and now we're going to talk about making the tangent planes for surfaces with the parametric equations. Okay, now let's catch up with what this is based in. So first of all, we've previously seen if you have a one-dimensional graph written in coordinates, meaning y equals f of x, we know how to write down the equation for the tangent object, which is, of course, that's a one-dimensional graph. So your tangent object is a tangent line. So at the point x0, y0, the formula for the tangent line is y minus y0 equals the slope at that point, f prime of 0, is f prime of x0 times x minus x0. Okay. Now we've also you've previously seen how to talk about the tangent line for a one-dimensional graph, which is written parametrically. So the formula for that, we could say it's r of t, and then the tangent line at the point r sub 0, which you can think of r as r of t0, and we can think of the original point as being x0, y0, z0. You could write it all those different ways. So that the formula for that tangent line, we would say L of t, if we like, equals original point, r0, plus tangent vector or direction vector, r prime at t0, times our parameter t. Okay. Now we've also seen that we can make, for a two-dimensional surface, written with the formula z equals f of xy, we can also get the tangent object for that, but since it's a two-dimensional surface, you get a tangent plane. So if you're at the point x0, y0, z0, we also know how to write down that equation. The equation for that tangent plane, written down one way, was z minus z0 equals df dx at that point, so fx of x0, y0, z0, times x minus x0, plus df dy at that point, so fy of x0, y0, z0, times y minus y0. So these are all things that we have seen before. So notice that you've got the one-dimensional written in coordinates and also one dimension written parametrically. We've got two-dimensional written in coordinates. So now we're going to do the next thing. Find the two-dimensional tangent thing, which will be a tangent plane, but when everything is written parametrically. And that's where we're at right now. So the formula for our surface is r, which we're going to call r of uv, which if written out, we could say it's x of uv, comma y of uv, comma z of uv. And we're going to be at some specific point on the surface, which we can say either is just r0, or we can say that there's some fixed point u0, v0, and we're taking r of that, or we can describe it in its coordinates x0, y0, z0. Okay. So I'm going to roll down, let's see, actually here. So what do we need? In order to describe this tangent plane, we've talked about this a little bit previously, you're going to need two direction vectors in the tangent plane. And as we've done previously, we form those tangent vectors by taking partial derivatives with respect to each variable. Now, in this case, the two variables that we use to describe the surface are u and v. So our function is r. We take derivative with respect to both variables. So we're going to have dr du, and that's going to be one tangent vector. And we're going to have dr dv, and that's going to be the second tangent vector. So let me just spread this out. You can see the whole picture. There we go. Okay. So first of all, let's just get familiar with this tangent vector idea. So so not drawn here is so what is drawn? So first of all, you've got in the graph on the left, as I previously said, we've got our region, which is a region of sort of UV points. And then U0, V0 is the point that's marked with the dot there. Next, by the function R that takes it into our three-dimensional space, which we call three-coordinate space, which we call XYZ coordinates. Now, U0, V0 gets mapped to that point. Make this consistent, we were calling this R0, okay? And that's R of U0, V0, so that's that purple or magenta point right in the middle there. Now recall that we've got grid lines. So at that point, whatever the directions the grid lines go in, the tangent vectors will point in the direction of those grid lines. And then of course, those two tangent vectors, as we've seen previously in just regular surfaces, those two tangent vectors will be in the tangent plane. Okay, so that when we take our dRdu and dRdv, we get those two tangent vectors. Now, once you've got two tangent vectors, which are in your tangent plane, in order to make the equation of the tangent plane, we mentioned previously that there are two different ways to do this. We only talked about the second one super briefly, but now we're going to talk about both of them in full. So one way to do it, which we've done previously, is take your two tangent vectors, take their cross product, and that gives you a normal vector. This is something that we've done before. So once you have the normal vector, we know how to write down the equation of the plane where we have a normal vector and a point. So writing it down here, just as a reminder, I suppose. So if we're at the point x0, y0, z0, you simply say x minus x0, comma y minus y0, comma z minus z0, dot normal vector n must be equal to 0, because they must be perpendicular, so the dot product must be 0. And then if you expand it, that gives you the formula for the tangent plane. Okay, that's one way to do it. And just as a reminder, n is a normal vector at a specific point. So in this case, it's necessary to evaluate it so that n is constant, so that n is comprised of constants. Okay, that's the first way. Now the second way, which has only been mentioned in passing before, we know that those two vectors are those two tangent vectors are in the tangent plane, so we can write the tangent plane parametrically. So how do we do that? So we're still going to refer to the tangent object as L, but now we're going to use the parameters S and T because it's going to be two-dimensional. So L of ST equals our original point, R0, plus S times dRdu. So parameter, which will be some number, times one tangent vector, plus T times the other tangent vector, dRdv. And I'll just mention, we've already used R and V as parameters for the surface. So just so as not to be confusing, we're going to use different parameters, S and T, for the plane. Okay, so notice what this means. This means that if I start with my original point, if I add a bunch of dRdu vectors, I'll still be in my tangent plane. If I add a bunch of dRdv vectors, I'll still be in my tangent plane. And if I add some combination of them, I'll still be in my tangent plane. And in fact, this describes the entire tangent plane. So if you've done linear algebra, you know this is just a linear combination of two vectors. That's the idea. But if not, that's fine. This is how we can get to any point in the tangent plane. Okay, so these are the two ways that we can make the formula of the tangent plane. Also, there's not necessarily a tangent plane that's well defined at a point. So the tangent plane exists precisely when our normal vector, which we make by doing dRdu cross dRdv, is not equal to the 0 vector. So the surface is called regular at a point where this is true and where we do have a tangent plane. And the whole surface is called regular if it's regular at every point. Okay, so that's the idea. Now let's do a calculation for a specific problem. So here's the question. Find the equation of the tangent plane to this surface written parametrically. R equals u cos v, u sine v, u squared plus v squared at this point. So R of 1 comma 0, if you plug it in, you'll get 1 comma 0 comma 1. And we're going to write the equation of the tangent plane in both parametric and in coordinate form. And then the last bit is find all the non-regular points for the surface where u and v go from 0 to 2 pi. Okay. So let's work it out. So to make the tangent plane, make the form of the tangent plane, the first thing we need are two tangent vectors. And we get those tangent vectors by calculating dr du and dr dv. So let's do that. So dr du, just calculating that, you get cos v, comma, sine v, comma, 2u. And we want the tangent vector at this specific point where uv is 1, 0. So plugging that in, you get you get that the tangent vector is 1, 0, 2. And the other tangent vector, dr dv, so now let's calculate dr dv. So calculating dr dv, we get negative u sine v, comma, u cos v, comma, 2v. And again, we want the tangent vector specifically at this point. So plug in uv equals 1, 0. And that gives you 0, 1, 0. And as we go through this, it'd be very helpful to keep track of which things are happening and being expressed in uv and which things are being expressed in xyz. It may take you some time to actually get used to doing sort of both of those at the same time and keeping track of which is which. Okay. So from this, we're going to make the formula for the tangent plane. And again, we know that we can write the formula two different ways. So first way, we're going to do it the way that we're more used to. We're going to write it down using the normal vector, and then it's going to be written down in coordinate form. So let's take a look at that. So we've got our two tangent vectors, and we know how to make a normal vector. We'll make a normal vector by taking the cross product. So I did slightly fancy. I just calculated the cross product from the original formulas themselves. In a problem like this, you can just take the cross of the two vectors at that point, just constants. But if you take it in terms of a formula, you get n equals ru cross rv equals this whole formula. Negative 2u squared cos v plus 2v sine v, comma, negative 2u squared sine v minus 2v cos v, comma, u. Okay. Now we're interested in the normal vector at this specific point, uv equals 1, 0. So plug that in, and we get the normal vector is negative 2, 0, 1. So we've got a normal vector, and we've got a fixed point. So from that, we know how to write down the equation of a plane. So the tangent plane is just, remember that our original point, now we're in xyz coordinates. So the point in xyz coordinates was 1, 0, 1. That was given in the question. So x minus 1, y minus 0, z minus 1, dot the normal vector, negative 2, 0, 1, has got to equal 0. And that's one way to write down the equation of the tangent plane, or we just expand it out. Negative 2 times x minus 1 plus 0 times y minus 0 plus 1 times z minus 1 equals 0. Or to do a little more simplifying, negative 2z plus z equals negative 1. And there's the equation of the tangent plane written in coordinate form. Now, method 2, which is going to be new for us. Writing down the equation, the tangent plane equation parametrically. So we know that the equation for the tangent plane, we just write down as xyz is going to be fixed point, x0, y0, z0, plus parameter s times 1 tangent vector, dr du, plus parameter t times second tangent vector, dr dv. Boom, 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 plugged in. There you go. That one's actually pretty easy because there's no more calculations to do. Okay. So these are two different ways to write down the formula for the tangent plane. Now, it is also possible to show that these two different forms are equivalent. Actually prove it by eliminating the parameters. We'll just take one look at how that works. So starting with the parametric form, we know that just reading out the three parametric equations, x equals 1 plus s plus 0, so we throw it away, and then y equals t, again, throw away the 0 stuff, and then z equals 1 plus 2s. Okay, so we can, solving for s, you get s equals x minus 1, and then just plug it in. So that gives you z equals 1 plus 2 times x minus 1. So z equals 2x minus 1. And then y equals t, so that stays on the side, and y can take on any value. And notice that z equals 2x minus 1 is the same as what we had before, negative 2x plus z equals negative 1. Same thing. Okay. So we've done eliminating the parameter before, but now we're sort of doing it in a new context, and also there's more parameters. Okay, so there's our first calculation of, given a formula for a parametric surface, find the formula for the tangent plane. And we did it two different ways. And then just to put one last thing on it, the last part of the question was to figure out where the surface is not regular and there is no tangent plane. So we calculated what the normal vector is in general, and it was this formula, negative 2u squared, blah, blah, blah. And so the surface will not be regular when that's the 0 vector. So this is not typically an easy, simple thing to solve, but this one works out really nicely. Just looking at the third coordinate, that immediately gives you u equals 0. So then plugging in u equals 0, we're just doing a bit of algebra here. So plugging in u equals 0, you immediately get that a bunch of things go to 0. So then 2v sine v must be 0, and then also 2v cos v must be 0. The only way for those to be 0 at the same time is for v to also be 0. So u and v are both 0, and then plugging that in to the original function, that'll actually just give you the point 0, 0, 0. Again, it's not just automatic, you actually have to go plug it in. So here was the original, here's the equation for the surface, and plugging in uv equals 0, 0, very quickly you just get 0, 0, 0. And so that's the point where the surface is not regular. And now what would it look like to not be regular and to say there's no tangent plane? Well, and in fact, what does it look like for a parametric surface to have a tangent plane? Here are some graphs to take a look. So here is the surface with its tangent plane graphed from two different perspectives. So this is the tangent plane that we actually found. So if you sort of check it out, you can see that that's, what was our point? Our point was 1, 0, 1. So x is, excuse me, x is 1, y is 0, and z is 1. So the tangent point somewhere over here, maybe a little easier to see on the second one over there, and there's the tangent plane. So of course, tangent plane to a surface looks the same as it did previously, but the calculation is a bit different because we're working with a parametric formula. And then also, what does it mean for it not to have, for a surface not to have a tangent plane? Well, you can see where the surface gets really weird. Right in there. You can see the surface actually intersects itself if you look closely and carefully. So at the point of self-intersection, uh, the surface is a bit nutty, and there's no tangent plane at that point. Next, we are going to consider our special case. So what if our surface is a function of two variables? So in other words, standard coordinate z equals f of xy. So, but we want to think about things parametrically. So how would we write something like that parametrically? So we can say r equals the three coordinates x, y, z. We can say that x is just u, y is just v, and and z equals just f of u, v. So basically, we've just said u equals x and v equals y. And of course, you don't even really have to use u and v. You can just use x and y. So now applying our parametric methods, what do we get? So dr du is really just dr dx. U and x are really the same thing. So looking at this formula, taking derivative with respect to u, you get one. You get derivative with respect to u of the first thing is just one. Derivative with respect to u of the second thing is just 0. And then derivative with respect to u of the third coordinate is just df du, which of course is really just df dx. And then similarly, the second tangent vector dr dv is really just dr dy, and in very similar fashion, you get 0, 1, df dy. Those are your two tangent vectors. Now, what's the normal vector? We've actually done this calculation before. The normal vector is just dr dx cross dr dy, and if you do it out, you just get negative df dx, negative df dy, 1. And therefore, using our methods, we can write down the equation of the tangent plane. So here I used the original point AB. Okay. Tangent plane, I should say. There we go. At ABC is x minus a, y minus b, z minus c dot the normal vector. So negative df dx at the point AB. Negative df dy at the point AB, 1. And that dot product got equals 0. Expand it out, what do you get? If you expand it out and then put the z minus c term by itself, you get z minus c equals df dx at the point AB times x minus a plus df dy at the point AB times y minus b. Once again, and this is the classic formula that we already know for the tangent plane. So once again, the classic formula in coordinates is a special case of the formula written parametrically. Classic coordinate formula. Okay. So next we're going to look at another special case. Our other special case is surface of revolution. So next, we're going to create a surface by taking the graph of y equals x squared for x goes from 1 to 2 and rotate it around the x-axis. And now we're going to find the parametric equation of the surface, and then also its normal vector. Okay, so first, let's make the formula for this, which we talked about previously how to do that. So we know that we're just going to let x be t. And so our radius function for the thing that we're rotating, y equals x squared, becomes t squared. So put that all together. The formula for the circle is going to be our function r is just t comma t squared cos theta comma t squared sine theta. And t goes from 1 to 2. Next, we'll make the normal vector. So to make the normal vector, first we need to calculate the two tangent vectors. So we need dr dt. So dr dt is just, if you calculate it, 1 comma 2t cos theta comma 2t sine theta. And then we need to calculate dr d theta. So calculating dr d theta, that's going to be 0 comma negative t squared sine theta comma t squared cos theta. Those are your two tangent vectors. Next, take the cross product. And that'll give you the normal vector. So taking the cross product, calculate, and you get 2t cubed, comma, negative t squared cos theta, comma, negative t squared sine theta. Okay. And then one last bit, let's also find the equation of the tangent plane at this particular point. When uv equals, okay, when uv equals 1, 0, and our point on the surface, if you plug that into the formula, the point on the surface would be 1, 1, 0. So that means we need to find our two tangent vectors at that specific point. So plugging in 1, 1, 0 into dr dt, and then also plugging it into dr d theta. And we already have our fixed point is 1, 1, 0. So writing it this way, you'll get the equation of the tangent plane written parametrically is a function, our plane L is a function of s and t, and it is the fixed point 1, 1, 0 plus s times the first tangent vector. If you plug it in, you'll get 1, 2, 0, plus t times our second tangent vector, which if you plug it in, you will get 0, 0, 1. And then alternately, of course, we can write it down in coordinates. So written down in coordinates, actually, let's see. So written down in coordinates, you'd first have to figure out what is the formula for the normal. Let's see. So the XYZ part would be x minus 1, comma, y minus 1, comma, z minus 0. And then we would need to take the dot product. And now we need the normal vector at that point. So plugging in 1, 1, 0 would give you 2, comma, negative 1, comma, 0. And that would have to equal 0. So there's the formula written out. Or if you like, you could we could work it out a little bit further. And that would give you 2x minus 1, 2x minus 1 minus y minus 1. And then there's a plus 0 times v minus 0. And that's got to equal 0. And then if you wanted to simplify it further, you would just get 2x minus y minus 1 equals 0. Any of those ways would be a way to write down the formula for the tangent plane, but in coordinates. And so that is that problem fully worked out. So to bring it all together, let's just summarize all the things that we did. Okay. So the parametric formula for a surface S, which is two-dimensional and has 3 coordinates, is R of uv equals x of uv, comma y of uv, comma z of uv. So we also talked about a special case where the surface S comes from starting with y equals f of x and rotating it around the x-axis. And in that case, we can write the parametric formula for the surface S as being, let's bring this around, okay, R equals xyz, and that's going to equal t, comma, f of t cos theta, comma, f of t sine theta. And in all cases, the normal vector to S is little n, and that's going to be calculated by first getting the 2 tangent vectors dr du and dr dv, and then taking the cross product. Next, the tangent plane. So if we have the surface S, we can write the tangent plane at the point r0, which would be x0, y0, z0. And we can write it in coordinates as x minus x0, comma, y minus y0, comma, z minus z0, dot the normal vector n equals 0, and then expand that if you like. Or we can write it in parametric form, which would be r, or typically we use L for this. L equals our initial point, r0, plus parameter s times tangent vector dr du, plus parameter t times other tangent vector dr dv. And then special case, which will actually come up quite a lot for us, is what if our surface is z equals f of xy. So not just, so yeah, so we can write it in that straightforward functional form. Then we can think, if we want to write r parametrically, the surface parametrically, we can say r equals u comma v comma f of uv. Really, u is the same as x and y, and v is the same as y. And then the normal vector is ru cross rv. But this, if we do the calculation, just works out to being negative df dx, comma, negative df dy, comma, 1. So the general case, and then also 2 special cases.